but actually this doesn't really apply to most of you because your class average was kind of abnormally high. Okay? But I'm going to emphasize. Keep in mind that not only that, there's another thing that after Unit 4 exam, when you go to Final 1, Final 2, there's no bonus activity, right? So for all those Unit 1 to Unit 4, you had bonus point. When you go to Final, it's just Final. So I'm going to tell you another extreme example that there was one student in the test, he was not 4.0 until Unit 4 exam, but after Unit 4 exam, he just reached 4.0. Okay? And I think he was like, he's accomplished his goal. Somehow he didn't really work for final. So he just went the final and final 2. From 4.0, he almost failed, which means technically he failed actually. But because he was 4.0 before final 1, he just got 2.0, just passing. Right? So this tells you like when you go to final 1, final 2, it's just only exam score, right? So in your mind, do not include any bonus point when you study for exam. Then you'll be glad that extra bonus point is there to help you, but do not rely on bonus point. Do you have any question about that? Yeah. During spring break, you're gonna have Unit 2 quiz to do at March 12th. I'm wondering if you are willing to move this on earlier date. The reason is that I want to post extra practice exam that was used for in-class quiz. So I wonder if you want to see that earlier than this date. If that's what you prefer, we can move this exam into quiz earlier. Otherwise, I'm going to post that after this date. Which one do you prefer? After? Yeah, you may still have like 3 or 4 more days to review the practice exam 2 and 3. I think that should be fine. Do you all agree? So do not change today.
How many practice exams are you posting?
2 more. That is including all of this.
I would be open to moving the due date up one day.
Yeah, on
but I don't
the
know
review
how other
day,
people feel.
on the review day, you're gonna. I assume you studied this one already on the review day. So there will be 2 more practice you're gonna have to study for exam, right?
Right.
So after review day, you have whole spring break. But this will be due during the spring break. After this, I think you make this a Thursday. The Friday, Saturday, Sunday, Monday, and then you have exam. So you have to use 4 more days.
That quiz is due on spring break at some point?
Hmm?
That quiz is due over spring break
Yeah.
on Thursday?
Yeah. But we can change that. If you want to have earlier than that, we can move earlier. If you want to have later, we can move later. I'm just giving you an option. Otherwise, I'm gonna keep that as it is.
I'd be down to move it up earlier.
Yeah,
Earlier?
so we can have the practice.
Okay. How many days earlier? 5 days earlier?
Yeah.
No, I was just raising my hand. Oh,
Oh.
Yeah,
From Tuesday?
Yeah, I would like, because a week from now would be the 10th.
yeah.
So, how many people are for moving today earlier? Can you raise your hand? More than half, okay. So there will be March 10th, I'm going to change due date. So that means I'm going to post this material earlier, 2 days earlier.
I thought when you said you were gonna move it earlier that you were gonna do it for Thursday. I was like, oh my god, I think I
On-
can do that.
This
Yeah,
Thursday?
this
No.
Thursday. Yeah, I was like, I have to work.
Oh,
I want to give you more time to study, that's
Yeah,
why.
yeah,
That's why I'm saying this.
Yeah.
So then, March 10th, all right. Do you have any question about this quiz?
This quiz is taking like 5 hours.
Do you have any question about this?
Yes.
Otherwise, we're gonna continue on the
I have a question on the last one.
last one. Nuclear reaction differ from ordinary. Okay, I have to see an option. What is that? Last one. So nuclear reaction is different from chemical reaction. Nuclear reaction energy involved per gram is much greater for nucleus. That's true. New elements are often formed in nucleus. That is also true. Nuclear reaction involve proton, neutron inside the nucleus. That's true. Do you have only 4 choice? No more do you have? Oh, I have. So nuclear reaction occur much more rapidly, not necessarily. So interesting. You don't want 5 choice. Anyway, does it make sense?
Yes. Can you also do,
What was the answer?
So I think the question is everything is true except one, right? So nuclear reaction differ from ordinary chemical reaction in all or one of the following way. So nuclear reaction is differ from ordinary reaction in all of 3, but this one not necessarily.
Oh, yeah, okay. Because of like radioactive decay or something, you can take that. Right?
What else?
So,
If not, yeah.
number 5?
Number 5, you mean 57?
Yes.
Okay. The band of stability described. Band of described. 57. Band of stability described. Band of stability described element contains the third periodic table. Now. Area within an atom where electron feel almost no attraction from now. Then the isotope that has a neutron to proton ratio of 1 for the lighter element and the neutron to proton ratio that equals to 12.52. Okay. A band of radioactive isotope on a plot of the number of neutron versus number of proton. This is more likely. If this one said like 1.6,
That was
I
the
would-
correct answer.
huh?
That was the correct answer.
It was a correct answer.
Yeah, I assume that's a typo though.
Okay.
wait,
Alright.
what?
A band of radioisotope on a plot of the number of neutron. A band of radioisotope on a plot of the number of neutron versus number of proton.
Because the reality is 1.52 in the book it says, right?
Okay. Other than number, there could be more because this one doesn't mean really bad, right?
They're not all, most of them are radioactive under 90 isn't radioactive in that though.
Which one?
A band of radioactive isotopes, none of them are even radioactive until uranium.
Right, if you're in the band, then they're not radioactive.
Yeah. I'm gonna make, if you choose one of these, I'm gonna accept as an answer because of the typo, okay?
Well, but because of the typo, a lot of us put none of none of the above.
'cause in-
Oh.
right.
Yeah.
That will be also accepted then.
Okay.
Alright, those three will be accepted. I'm gonna go correct in the answer as, all three will be accepted, okay?
Thank you.
This is.
That makes sense.
It's all 1 point.
Yeah,
Are you allowed all 100% please? Think about all that.
okay, so we know that nuclear reaction happen whether through 5 basic decay, alpha, beta, gamma decay, electron emission, electron capture, or through the nuclear transmutation. What is nuclear transmutation, by the way? That is different from decay. Those 5 kind of decay just happen when you have one singular nuclear that decay. But nuclear transmutation is you have heavy nuclei and then you bombard with a certain particle, either alpha or neutron. That's nuclear transmutation. When that happens, there's energy released from nuclear reaction. And this is where famous Einstein equation play important role here. When chemical reaction happen, A reacted with B becomes C. Is there mass change or not? So does mass conserve after reaction or after and before reaction or not? So mass stays same. That's how we learned the Chem 1, right? That's what Dalton said. And then we still accept it. But rigorously from Einstein theory and then reality, mass doesn't preserve. Mass will change. Okay? But that change of mass is so tiny, we wouldn't notice it for regular chemical reaction. But when nuclear reaction happen, like in this example, when nuclear reaction happen, the mass change is kind of detectable. You can detect there's a change of mass, and then that will associate with energy, because that mass change noticeable, it will release huge energy. Okay. So we are not worried about chemical reaction, although there's a mass change, we're gonna ignore it. It will be only just a nuclear reaction that have a significant mass change. And then once you have mass change, then change in mass times speed of the light squared. That's what energy we're gonna have. And this will be huge energy. For example, this is actual reaction that can happen. And mass of thorium is over here. You can look it up your PI table and then get the number, but this is more digit than most PI table have. And this is mass for helium. Before reaction, uranium has that much mass. So if you do subtraction, there'll be a tiny, a little bit of mass change. This is like a 4 milligram, 4.6 milligram. So obviously you can detect it. So the reason that most of your lab balance can measure 3 decimal, right? And if you use analytical balance, you can detect 4 decimal. So even from your lab, regular lab, you will see the change of mass. So that's very significant. So that mass change with when you use Einstein equation, we're going to convert that gram to kilogram. So 1 kilogram is equal to 1,000 gram. So with this factor, you're going to have kilogram unit, and then multiply speed of light and square. Then this is the number you're going to get. And the unit for energy is this, but more standard unit is joule. So this unit joule is equal to that unit as well. So this will be really huge energy that you can use for, many good purpose. Sometimes tragedy can happen using this energy with the evil purpose, like atomic bomb. So formula you use for energy generated from nuclear reaction is E to the mc square. So why don't you try to find out energy that will be released from this reaction? So you already have information about mass of each particle. So why don't you try to find the answer is already here. So why don't you try to get the same number?
Can you walk us through what you did?
Yes.
Okay.
So to use this formula, so Einstein equation is what you have to memorize it. E to the mc square. Okay. Mass change is mass of later mass minus initial mass. So you will find out that as mass change. I have a negative sign, which means mass decreased. To use this equation, mass should be have kilogram unit. But we have atomic mass unit. When you think of hydrogen there, hydrogen mass is 1.0008, but that is averaging all possible isotope. So if you just think most typical hydrogen, which means 1, then mass number will be just 1 AMU, right? If you look at the hydrogen, that will be 1 AMU. But we know when you have 1 mole of hydrogen, 1 atom, 1 hydrogen atom is 1 AMU. When you have 1 mole of H, it will be 1 gram. Right? So number on the periodic table means two things. If you have 1 mole, that will be 1 gram. But if you have 1 atom, that will be 1 AMU. So from here, you can say, if I have Avogadro number, because 1 mole means Avogadro number, right? 1 mole means Avogadro number. So if you have Avogadro number of 1 AMU, that should be equal to 1 gram. That's why you can use this conversion factor. 1 gram is equal to Avogadro number AMU. Okay? This is a convenient relation you can use to convert from AMU to gram. So after that you have unit of gram, then you can convert from gram to kilogram. We need kilogram unit to use that formula, and then multiply by speed of light. I think this is the part you may have to understand why this relation is true. Because 1 atom hydrogen will be 1 AMU, but when you have an Avogadro number of a hydrogen atom, there will be 1 gram. It's the same number, just different unit.
Why did you have to convert it to kilograms? Why couldn't you leave it in grams?
The reason is that any physics equation use SI unit, and the SI unit for mass is in kilogram. Gram is not standard unit, it's kilogram.
Okay.
Chemistry we use gram for many formula. In physics, kilogram is the unit, that's a standard unit.
And then you just memorized the 3 times 10 to the 8th?
Oh yeah, so
Okay.
speed of light is what you have to memorize. This is a universal constant you have to memorize it. You don't have to memorize actually 2.99 something. You don't have to memorize 3.0 will be fine. Okay.
You square the speed of light before you
Yeah, we're gonna have
first.
Yeah, we're gonna have to scale. Yeah, we're gonna
You
have
do
to-
that before you multiply it by the kilograms.
Yes, but you. Yeah, that's right.
Okay.
Helium is made of helium. I don't say alpha particle. So alpha particle is made of 2 neutron and 2 proton, right? So if I draw alpha particle inside the nucleus, you have this. What if I have just 2 proton and 2 neutron? Which one is heavier? Having these 4 particles separate or together, which one is heavier?
Oh, they're heavier separate, aren't they?
You have it separate.
Because of the speed
Think.
of light. There's something to do with energy and the speed of light together.
Yeah. I mean, what you said is, pretty much right.
Yeah.
So when particles are together, when they are separate, it's heavier. Okay. So how do they know? Well, this equation is something to do with that guy, right? Einstein equation. So they somehow found out mass together is somehow lighter than separate. So that difference is what they call mass defect. Mass defect. Okay. when you put some particles together in the smaller space, somehow you are losing mass. Somehow you lose mass. So that's called the mass defect. And then that change of mass can be used in the Einstein equation again. That mass defect times c square. There will be again huge energy. And then also, when you separate, so this is the energy difference between those two situations. So that's one definition, one interpretation of this energy. Another interpretation of energy is you try to separate this guy far away from each other. You have to use certain energy, okay, to separate it. That's the energy exactly same as this energy. Okay? So when this guy come together, it will release huge energy, but that's the energy you need to separate this guy far away from each other. And then we call that as binding energy. Why? Because that's the energy you need this from binding to far away each other. Okay? It's binding energy.
So we don't know what explains that phenomenon. We just have to know that it occurs.
Basically, so in the ancient times until like 19th century, we thought particle is one thing, radiation another, and the energy is something from the mass. But Einstein found out that energy and mass are not separate things. So relative theory is quite deeper than what we say at E equal to mc square. But basically it's all related to this equation. So mass, anytime mass decrease, energy increase. And then when you put more energy, it becomes heavier. For example, this is not relevant to this what we do here, but Einstein theory says this guy may have certain mass right now. If I throw this guy, it has kinetic energy there, right? Because it increases kinetic energy, actually it increases mass as well. But you don't have to know. Also, if I have a spring has a certain mass, right? And if I just either stretch or compress, then I'm putting some energy into spring, right? Mass of spring increase by that much. But you do not see that because whatever I do, my energy into spring is very small. And then you still use Einstein equation. Let's say I put in like 10 joule into spring to compress it. Then you divide by speed of light squared. That's the mass change. The spring mass is increased really tiny bit, then you may not notice. But Einstein law actually go everywhere. Okay? But you don't have to know spring or flying object. Just focus on nucleus, okay? So if binding energy defined by how much energy you need to separate this guy, then what do you think between helium and carbon? This is carbon because atomic number 6, that's number 12. When I separate all of this guy, and then when I separate all of this guy, which one requires more energy? Is it helium, alpha particle, or carbon? That's carbon, right? Because I have to separate a lot more particles. Binding energy for carbon will be higher. So comparing which one has more binding energy, it's like two simple questions. So we divide it by number of nuclei. Nuclei means number of proton and neutron. So for helium, you find the binding energy and divide by 4. For C12, find the binding energy divided by 12. That will be only more like a fair comparison. So binding energy per each nucleon. So that binding energy comparison is coming right here. This is atomic number from 1 through all those possible elements. And then binding energy divided by number of nuclei. If you look at it, iron is most stable element. Okay? Because binding energy is highest at iron, and then other element nearby iron is almost similar binding energy per nucleon. Now hydrogen, this guy is very low. Uranium is also relatively low. Because of this reason, particles that lighter than iron, if they have any chance, they will come together, make a heavier nucleus. That's what we call fusion. And then element that is heavier than iron, if they have any chance, they try to split into a lighter nucleus. That's what we call fission. Okay? So mass defect is again mass difference between mass altogether and mass of individual particle. So for alpha particle here, we can find the mass defect based on mass of each proton and neutron, so right side, and minus mass of nucleus, this guy. Or mass of nucleus is, you can just write as atomic mass minus mass of electron, right? Because mass of nucleus do not include electron. You can subtract that number from atomic mass. Once you have mass defect, you can just use Einstein's equation, delta E equal delta M times C squared. But oftentimes they will ask binding energy per nucleon, then you divide by that number. That number you found out by number of nucleon. Number of nucleon. Okay?
Well, we can just use 3.0 times 10 to the 8. We don't have to use 2.999, whatever.
That could happen. 3.0 is good. So why don't you use it now?
So it's just the mass difference, and then to gram, or to kilograms, and then times the speed of light. So
Exactly. I don't know the number is 26 proton, 30 neutron. Okay. So 30 neutron. Proton. That is for individual particle minus nucleus. Right, one more. Mass of atoms something. What number is that?
Zero point five two.
0.52?
0.5284.
0.052?
0.5284.
5 to 84. Can anybody confirm? Right. So that's delta M plus or minus? Plus.
The individual ones are bigger.
I think they did plus, right? That should be right. There you go. So delta E is delta M convert to gram and convert to kilogram again, and then multiply speed of light squared. Then you have one number divided by 6.022 divided by 1,000 times 3, 8. I got 7.897 minus 11. They are asking the binding energy per nucleon. So binding energy per nucleon is that number divided by total number of nuclei, which means 56. Then we're gonna have answer like this. Okay,
Wouldn't that say 0.5284 AMU?
say again.
Wouldn't that go down to 5 significant figures after the decimal point?
Here.
Yeah,
So what do you get?
a 0 on the ends, because it goes to 5 decimal points for the addition, subtraction.
Oh, even though the significant figure calculation, right?
Yeah.
Okay, I think I trust you. Yeah. Yeah, right. So I used only just 4 sig fig, but what you say is one more sig fig, right?
Yeah.
Yeah. I think that should be right. Is that right?
Yeah. I, not Y.
Aye. Yeah. Right. So yeah. Consider sig fig, there should be one more digit. So what number do you get?
I'm still running calculations.
Okay, all right. So that's how you did. Okay. What he said is more accurate. Okay. Yeah. But the thing in the end, if you're gonna use scalar line as this guy, this will limit your sig fig. So you're gonna end up having 3 sig fig just like that. Okay. But obviously, if you use more accurate speed of light 2.99 blah blah blah, then we get us like a 5 sig fig. Okay. Any question?
And that's per one nucleus.
For one nucleon.
Okay.
So we call that a nucleon for one nucleon.
So
Mm-hmm.
the light energy. You divide it by 56.
Yeah, 56 because the mass number 56 means you have 56 nucleon, proton and nucleon, proton 26 proton, 30 neutron together.
So the energy we're coming up with is per particle, per proton or per neutron?
So energy is coming from difference of mass.
Yeah.
difference of mass. But if you have more particle, then obviously you're gonna have more mass difference. You're gonna have more energy. So we are dividing by the number of nuclei. We wanna see how much energy coming from each, on average, from each nuclei.
I guess not follow, because I thought we had, I thought we took into account all the particles already in the calculation in the nucleus.
Yeah. So this energy is coming from this is a binding energy associated with iron 56.
Right.
So when you have iron 56, one atom, actually one more, because we are using gram here. If you have one more of iron atom,
Yeah.
no, not really. Actually, one atom, one iron atom, because this is one iron atom. So one iron atom will have this much binding energy. Okay.
And the,
Yeah, go ahead.
okay, it's because the question said nucleon, like per particle, right?
Yeah. Well, in this question,
Okay.
they are asking energy per nucleon.
Right, okay.
So once you have find the energy, you divide it by total number of
I was,
nuclei.
I'm sorry. I
Because they often ask question like this.
Okay.
So you have to read carefully, because if you after you find out binding energy, you may just stop right there, but you have to be careful. Sometimes they ask per nucleon, then you're gonna divide it by number of units. Okay. Now I move on.
Just one more thing for clarification.
Yeah,
So,
sure.
Per nucleon, a nucleon would be either a proton or a neutron.
Yeah, so we consider they have same mass.
Right.
Although rigorously there should be a little bit difference, for this calculation purpose, we just view as the same mass. Alright. This is practice I want you to practice class. So this is slide, actually I explained it. So iron is more stable in terms of binding energy per nucleon. So any lighter element than iron, whenever they have a chance, they will come together, that will be fusion. Any element heavier than iron, if they have any chance, they will split, that will be fission. Okay? So let's go over nuclear fission first. Like a uranium or other heavy element, if you just use neutron and they shoot to this nucleus, they will split. And then that will start a nuclear fission. And that will give us huge energy. That's the principle of nuclear power plant or atomic bomb. So you have uranium-92 and then use a neutron. You could use alpha particle, but if you want to use alpha particle, you have to use high energy because they have same charge. So using neutron is more efficient. And then when neutron hit this guy, this will split into like a two element. It doesn't have to be always krypton and barium. You may have different split. Okay, this is one example how they split. And when they split, it will create 3 neutrons. So each of neutron will again attack neighbor or uranium. And then that uranium will split like one of these. And then also it will generate another 3 neutrons. So this will exponentially split a particle. And then there will be the nuclear explosion.
Is there
What
any
the-
reason why it's just 3?
That is coming from, so you already did the nucleation balancing left and right side, right? So when you just balance that, it should be 3 neutrons on the product side. If you have 2 or 1, it doesn't balance it.
Oh, another reaction could have 5.
Probably, yeah. If you use different different like a nucleus and you bombard with like a neutron or other particle, there'll be some other case you may have 4 neutron. Yeah, that's possible. But the thing is, so after first neutron hit uranium, you will have like 3 neutron coming out, right? But if you have, size of uranium is not big enough, next neutron may just escape the surface. So not being able to chain reaction. You should have at least certain size, so that next neutron can hit another neighboring uranium. So that minimum size is what we call critical mass. For uranium, it will be like 2 pounds, around 2 pounds, which is 1 kilogram. So if you have uranium on both your hand, this will be less than critical mass. That doesn't explode as a nuclear, bomb. But if I put together half kilogram on left side, another half kilogram in my right side, put together, it will explode. It will blow whole Lansing and maybe mid-Michigan all together. But the thing is, I won't be able to hold it until it explodes. Before it explodes, I may just this radiation will kill me right away. So I may just drop those guys into another 2 half. Okay? So that's why some evil people just devised atomic bomb. So half of mass, critical mass is on one side, another half of mass is on the other side. They'll just make them come together. Okay?
Does critical mass come from your collision model theory? Or does that have nothing to do with it?
Yeah, it could be relevant because the neutron produced from one fission can hit another neighboring neutron. So that should be a collision. I can say that. So so from here, so produced neutron can hit the neighboring uranium again, and there will be another three, which means three give next three, another three, that means the exponential function, right? So neutron will produce exponentially. So you want to slow down this if you want to use.
Hey, I grabbed the bottles right here.
Oh, yeah, sure.
Do you have any of the other,
Huh?
we don't have an F,
Which one?
the F?
F.
Probably not.
No, I don't
Alright,
know.
thank you.
Because this exponential increase of neutron is too much. We want to control it if we want to use this one for peaceful purpose. Okay? That's why we call nuclear reactor. And nuclear reactor is important to control production rate of neutron. If there's too rapid, it will just bomb, okay? Nuclear bomb. So you want to slow down that. That's what control rod is. So in the nuclear reactor, we're gonna just briefly review what nuclear reactor is. So this is a reaction reactor core. This might be uranium. And then when they start nuclear reaction, you have to somehow absorb too much neutron coming out of this guy. Okay? So this is what we call control rod. So control rod will absorb some of neutron, so it doesn't go too much exponentially. So we can just make this reaction go slow, and then we can just get the energy for power generation. So this is control rod that just absorb extra neutron. And here, there is water just coming through this nuclear reaction core, reactor core. This is water, but it's pressurized water. So pressurized water or liquid sodium. So that guy will take heat out of reactor core. That will be extremely high temperature. That water will boil regular water into steam. That steam is what rotates turbine, and then that generates power. So this boiling water and the steam turning turbine is just general principle for any power generation. Okay. Only difference for nuclear reactor is you have reactor core right here, and then you're gonna use control rod to absorb some of the neutron, extra neutron. Now this pressurized water have role as cooling reactor, which means we call that as cooling fluid. You can use water, but not regular water, because this is too much heat there. Water evaporates right away because the temperature is extremely high. Any water will become just steam right away. But if that is water used for in here, you have to keep that as still liquid phase. You have to use a lot of pressure to keep that as liquid form. So that's why we call that as pressurized water. Or you could use liquid sodium as well. Sodium is metal, but this temperature is so high, the sodium metal turn into liquid. Liquid sodium is good, but water is cheaper, and you can use in any place. So pressurized water is more common in nuclear reactor. Now that water is not only used as the cooling fluid, that also used as moderator. So moderator is the opposite of control rod. The control rod actually slow down reaction. But moderator is, so this water will slow down neutron, but it slow down velocity. Control rod slow down neutron, so it actually remove neutron. Okay, it remove neutron, so it slow down reaction. But this one slow down the speed, not reaction. So if neutron goes slower, that means there's more chance it can continue chain reaction. Because if neutron is too fast, it will escape from the surface, right? So by slowing down speed of neutron, actually nuclear reaction keep going. So that has opposite law. Control rod and moderator has opposite law. Okay. Now the nuclear reaction is really useful for generating energy. What do you think is the problem of nuclear plant? What problem do you see? If that's real, because in terms of energy generation, nothing can beat nuclear reaction. This is the most productive way to generate energy. But do you see any problem with that one, nuclear reactor? I mean, you see that a lot of accidents in nuclear plant, and also after you do a nuclear reaction, the nuclear waste will release harmful radiation for so many generations. So you have to somehow put this nuclear waste somewhere. Where are you going to put it? Because this radiation just penetrates anything, right? So you cannot keep that in any regular place. You have to put like a deep down in the sea, or you have to use you have to confine inside of deep down earth using like a red containment. But even with that, nuclear it will go like several thousand, several 100,000 years. Okay, so there's a problem for nuclear reactor because of that, they are looking into how they can use fusion instead of fission. Because fission has a lot of issues. Fusion is you just use hydrogen isotope. This is deuterium. This is tritium, but they are both hydrogen. So we have hydrogen plant in the ocean. Using those hydrogen, if you just combine together, which means fusion reaction, you generate helium and then energy. If you look at the product side, nothing is harmful. Okay? Nothing is harmful. So this will be really attractive compared to current fission. The only problem we have is this reaction is hard to achieve. The minimum requirement to have this reaction is you have to have 40 billion Kelvin. You have to achieve temperature up to 40 billion K. And then no one can make that temperature other than sun itself, right? So in nature, this reaction happens only in sun. So you have to somehow create sun on Earth. But if you really create sun on Earth, Earth will just melt away. But they still try to create this reactor. Basically, it's like an artificial sun in small size. And they are so far able to it's called tokamak fusion reactor. So many countries work together to achieve this. Right now, as of 2017, they could reach 70 billion Kelvin for 72 seconds. But if this gonna be any useful, this should last like at least several hours, several days, several weeks, right? This is too short. But people are doing this one and they actually achieved a lot so far. I think right now, in 2020, I guess we may have reached several million. Okay? We are getting there. So once we have it, we really have like these are a lot of energy issues. Okay. Wow. We are done. Do you have any questions?